Let's begin. I want to finish with discrete distributions today. I want to make a comment first about your Jupyter notebook and homework submissions. So a Jupyter notebook is a type of document format like PDF. And you can open it using your Anaconda distribution or Google Colab or Visual Studio Code, right? It doesn't matter where you open that Jupyter notebook. As long as you can open it and put code and text, some of them might have like nicer looking interpretation of what it looks like. I don't care, right? Just do it in whatever platform that is comfortable for you. It doesn't have to be on the Jupyter Notebook Anaconda distribution, okay? So as long as it's a Jupyter notebook to ease out the blending of coding, text, and displays all in one place together. So, if you're having trouble with your Jupyter notebook locally or CHPC is not working, just hop on Google Colab and just move your notebook there or start editing there, okay? So it doesn't matter, don't worry about that. I really don't care where you create your Jupyter notebook, okay? So I hope that helps. If you have any concerns, I've had some questions about that. I don't care where you create your Jupyter notebooks as long as you're able to get them and do them. And if there's any issue with your homework, you're unable to convert to PDF, sometimes it happens. You need to let us know early so we can just work with you. So you can send us the notebook, for example, and we'll be able to try to convert it for you in worst case scenario. But just let us know, okay? Don't be an island and feel like you're not asking for an extension or anything like that, okay? You're just saying, hey, I'm having trouble with the notebook conversion. FYI, and yeah, we'll work with that. Don't worry about it, okay? Last time we talked about the binomial distribution and we plotted it, and if you remember, the binomial distribution was counting the number of successes, that's your x in the binomial formula, given n trials. So you flip a coin 50 times. 50 times, how many successes do you get? What's the probability of getting 10 successes or 5 successes? And you define what success is. Success could be heads, success could be tails, and you give it the probability of each trial. There's only 2 outcomes per trial, success or failure. And when we left off last time, we asked the question, what happens when the probability of success is low? What happens to that graph? So you're going to have much less number of successes. So the peak is going to be here, closer to 1, 2, or 3, or 4 successes. But when you have a high probability of success, then you're going to pack a larger number of successes. So the distribution is going to move to the right. Otherwise, it's going to be symmetric in the middle. Okay? And we'll continue with that. We're going to do some problems. And these problems, they're easy. They end up being just kind of mechanistic. And you'll see in your homework assignment, there's 10 problems. I'd be surprised if it takes you more than 30 minutes to finish the homework assignment. They're just really low-hanging fruit, but they provide the practice which we will need later when we get to confidence intervals, okay? And you'll see what I mean in a second. So we'll do some problems with binomial distribution and to introduce some new concepts of what we mean in certain probabilities. We'll start with the first one. What's the probability of getting exactly 6 heads in 10 coin tosses? We assume it's a fair coin. We demonstrated earlier that this experiment is a classic binomial, and it's a classic experiment that can be modeled with a binomial distribution. With nothing said about the coin, I'm going to assume that it's a fair coin. So my probability of success is 50%. And that being said, we'll say that the number of heads getting a head is a success, and to count 6 successes in 10 coin tosses. So I have 10 trials, 6 successes. So what I'm calling the binomial excuse me, probability mass function 6. What's the probability of 6 successes in 10 trials with 50% chance of success? That's what I'm asking. And you can write it mathematically with the standard formula that we want. So always think in terms of probability. P of x equal exactly 6 implies binomial distribution 6, semicolon, 10 trials, 50% per trial, and then you can evaluate the formula or just plug it into your notebook. I'll do this in the notebook, but then we don't have to continue doing this all the time. And so I could do, so what was my, so I already declared my binomial, so I'm going to call another one, and I can say binom.pmf, and six successes in 10 trials and 0.5% probability. That's going to give me a number. Okay, that will give me a number of 20.5%. Okay, just like the analytical formula on the slides. All right, so you're welcome to use Python for this, and eventually what you can do, you can build a little calculator to compute binomial distributions and to compute binomial probabilities. For input, you'd have to provide n, p, and what probability you're looking for. Now, not all questions are going to be p of x equals 6 or equal 5. We're going to see other questions. What is the probability between two numbers, or greater than or less than? So you have to reason about all of those. And we're going to cover all of these examples. Here's another example. Again, these are taken from the textbook. I think you'll find the PDFs on the canvas. A quality control expert at a large factory estimates that 10% of all batteries produced are defective. Okay? If he takes a random sample of 15 batteries, what is the probability that exactly 2 batteries are defective? So 10% of all batteries produced are defective. That gives us an idea that the likelihood of just randomly picking a battery from the assembly line, there's a 10% chance that it being defective. Okay, so if we call being defective a success, we can probably assume that there's a binomial distribution here. Why? Because the batteries, they're either defective or not, either successful, defective, or not, with the probability of success being defective is 10%. If wording defective is not consistent in your mind with the word success, okay, then swap the meaning. Say battery being not defective is success, probability of success is 90% in that case. So either one of those, okay? But as long as you're clear with that. And here's some just kind of verbosity about why we justify using the binomial distribution. But the point is, I have 15 trials because out of 15 batteries, he's going to pick 10 of them. Out of 15 batteries, there's a 10% chance that that they're defective, 10% chance they're defective. And what's the probability that exactly 2 of them are defective? And you call the binom PMF at exactly 15 trials with a probability of 10%. And you get a pretty good chance, 26.7%, that 2 of these batteries are going to be defective. Okay. Now, I'm going to take this up a notch. Again, the same problem, quality control expert at the large factory, 10% of the batteries produced. Someone's bottle here. Okay. I don't know about you, but like when I see a random bottle sitting somewhere, I can't touch it or like hold it or move it. And it just feels gross for some reason. I could pick up, if you see something on the floor, pick it up, throw it in the trash. But like a bottle and, someone, I don't know, I can't like get myself to touch it. It's weird OCD or something. Anyway, so what's the probability? Okay, if he takes a random sample of 15 batteries, so we're still doing 15 trials, okay, 15 batteries. What's the probability that no more than 2 batteries are defective? Okay, now you have to think about that in terms of probability. No more than 2 are defective. So at most, 2 batteries are defective. It could be 0 batteries defective, could be 1 battery is defective, or at most 2 batteries defective. So you have to express this mathematically by saying that I'm looking for the probability that x, my random variable, the number of defective batteries, is less than or equal to 2. As I said, no more than 2. Right? But it could be 1, it could be 2, it could be 0 batteries. So now, since x is a discrete random variable, this is equivalent to adding the probabilities. I want the probability of 0 defective or 1 defective or 2 defective. So once you see a less than or equal, you are going to be adding probabilities all the way up and including that number that you're looking at. Okay, so in this case, this would be all of these probabilities. Because this is discrete, it's easy. You know, we have discrete successes, 0, 1, 2. There's no numbers in between. When we go to continuous distributions, this will become an integral. Okay, we're going to be integrating from 0 to whatever number you're at. Visually, visually, this is the distribution that corresponds to this problem. Binomial, these are the number of successes, okay, with 10% chance of finding a defective battery. So there's a high likelihood here of finding a defective battery, but then you're not going to find 7 defective or 8 defective batteries. But, you know, by 3 batteries, that probability starts going down. But this problem we're looking at no more than 2. So we're looking at this bar, and that bar, correct? So if I highlight those on the keynote, those 3 bars represent my probability that I'm looking for. Yes?
Would you say that this is an OR statement, like probability?
Yes. Yes.
For probability distributions, you do not have to worry about overlapping.
There's no overlapping for discrete. Okay? When you go to continuous, there's also no overlapping, but it becomes an integral. But then with continuous, you'll see less than or equal or less than are the same statement because there's no single discrete value. But for discrete distribution, less than or equal is going to be different than less than. We will see in the next example. Yeah, good point. Yes, this is exactly equivalent to an OR statement. So you're saying no more than 2, probability less than or equal to 2 batteries. Then it could be 0 batteries, could be 1 battery, could be 2 batteries. All right? And when you add those up, you will get that probability. So, you know, we can do this in Python, but then this is an example where you would declare your binomial distribution once, like I said, store it in a variable, and then call it 3 times on binomial PMF0, binomial PMF1, plus binomial PMF2. Okay? But there must be a better way, because a lot of probability problems are going to be nasty like this. What if I had 700 trials and I'm asking you for the probability less than 300, right? It's just, you can do a for loop, let's say, to add all of these up, but you know, there should be something that we can do automatically that gives us the answer. Do you remember something we did early on where we were building relative frequency distributions and frequency distributions? There was one time when we started adding them and we said, oh, 60% of the people make less than $80,000 in the salaries, right? Do you remember that example? We called it cumulative frequency distribution. This is exactly what we want here. If there's a way, or if Python or the math can describe that, oh, is there a function that can give me just this cumulative number up to a number? Turns out, yes, that this is actually a mathematical property of probability distributions, and it's called the cumulative distribution function, or for discrete variables, the cumulative mass function. And what it does, the CDF, cumulative distribution function, it represents the probability that P of x is less than or equal, so strictly inclusive, of a certain value x, and it evaluates all the probabilities from 0 or from whatever that for things begin, all the way up to and including the number of interest. So in special cases for the discrete distribution, the CDF is sometimes called a CMF, cumulative mass function. So this is a great example where I would say, oh, for this problem, this is equal to the CMF of the binomial at 2. Because the CMF at 2 is going to give me the probability of P of x less than or equal to 2. Okay, it's just going to add those up for me in a GIF. All right, and it's a built-in routine indeed. Mathematically, we refer to the, if we use a lowercase symbol for the probability distribution, whether be it discrete or continuous, the cumulative distribution, we refer to it as a capital letter. Okay, so if we use B, the symbol B, to refer to the binomial distribution, when you see me use the word capital B, I'm referring to the cumulative binomial distribution. So capital B at x equal 2 is equal lowercase b at 0 plus lowercase b at 1 plus lowercase b at 2, okay, and so on. Right? In Python, this is great. It also, there's a function that does that for us. And instead of calling binom.pdf, .cmf, PMF, you call binom.cdf. And that's it. That gives you that cumulative distribution. And the best part, again, you can also declare this once and for all, okay, and then call in the CDF, okay? So let's go ahead and take a look at that CDF and what it looks like. Ew, 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 ew. Okay, I'm exaggerating all this a little bit. Thank you. Okay, so I'm gonna come back here to this distribution. I'm gonna make it a little bit more. Let's do 15 and equal 15 and put 0.1 over here. I'm gonna plot this again. Okay, let me delete this. And next, I want to do a bar chart of the cumulative distribution function. Cumulative distribution. I'm going to call binom.cdf. Okay, you guys in the back can see? And a lot of squinting. But this, okay, binom.cdf. And I'm going to call this on the x values and np as well. I call this x values and np. And let's plot it. Qtl plot, plt.bar, and then x values and cumulative values. Okay? What do you think it's going to look like? So at the first value is going to have exactly the same value, correct? Yes.
Is it going to kind of look like a square root function?
Yeah, sort of, yeah. So do you know what that means? It's going to start low at this value, but then we're going to add this value to that value, so it's going to go up a little bit. And then we're going to add this to this and that, and it's going to go up a little bit. But then what happens? Peaks out at 1. Why 1? Okay. And the sum? Yeah. So eventually, let's take this example. Once I hit 6 or 7, the probabilities here are 0, almost 0, right? But the sum of all of these preceding them should be no more than 1. So then you're adding 0 to 1, 0 to 1, and you're going to peak out at 1. Okay? So let's see that. There you go. Very nice. Okay, we start over here. This first bar is exactly the same height as this bar. It's like 0.21 or 20.5%, right? It's exactly this one. But then this guy is going to be what here is giving us about 55%, right? So that's the addition of this guy, 35 plus 20 point something. That's about 55%, correct. So you're just adding them together. And then when you go and say, oh, CDF at 2, it's essentially getting you all the values of the PMF of 0, 1, and 2. Okay, adding them all together for you, so you don't have to keep calling the PMF over and over again. So for the example that we just did, I would do binom.cdf, and we had x equal 2, so no more than 2 batteries, and we had 15 batteries and 0.1 success, and that's equal to 0.815. That's equivalent to binom.pmf of 0, 15, 0.1 plus binom.pmf 1, 15, 0.1 plus binom.pmf of 2, 15, 0.1. Agreed? Look at that. Okay. Good. Sanity check. Makes sense. If it doesn't make sense, raise your hand. Okay. It's just a way to compute these less than or equal probabilities. Okay. Whoops. let's continue. So this is a bar explaining what I showed you just now. Next, I'm going to ask you a bunch of questions about visually interpreting what probabilities are going to mean on the graph. So what does this correspond to? The probability. So I'm taking all yellow, yellow, yellow bar, yellow bar, yellow bar, yellow bar. So all the bars are yellow from 0. So I'm picking all of these, the sum of all of these probabilities. That's the probability of what? That x is less than 6 or less than or equal to 5. So Alex, why did you say less than 6? So is probability less than 6 equal to probability less than or equal to 5? Yes, 100% in the discrete distribution. Correct. So what would that be in terms of capital B? Just say capital B at what value? X equal 5. Correct. Okay. So that would be capital B at x equal 5. All right. So what about these guys? Okay. Probability of x less than or equal to 8, or probability x less than 9. We'll do this next. What value for the CDF this would be? Capital B at 8. Correct. Okay. Very good. What about this guy? In terms of probability, Benjamin?
1 minus less than 10.
Okay, or the probability of x greater than or equal to 10, or the probability of x greater than 9. But the CMF, the CDF, how do you calculate that with the CDF? The CDF, remember, doesn't go to the right. The CDF computes everything to the left. So how would we do this with the CDF?
Like you said, you would do 1 minus because the max of the CDF is 1.
Okay, so all of these bars, they sum up to 1. Agreed? So if I were to sum up all of these bars, they sum up to 1 because this is a probability distribution. If you're thinking about this only geometrically, in terms of like size or area, the total size, the total area of these bars is 1. I want the area of these bars. I know the total area, and I know the area of these bars, right? Because that's what the CDF does. So if I were to take 1 minus CDF at 9, I'm going to get these guys. Okay? This is the equivalent of saying also that these bars, or this probability of x greater than or equal to 10, is equal to 1 minus the probability of x less than 10, or 1 minus the probability of x less than or equal to 9. Okay? All right. Now, P of x greater than 8, which bars are those? Yes? No, just highlight the bars. Just point the bars to me. Which bars? Okay, 9 through the end. So we start exactly at bar 9, not bar 8, because it's strictly greater than 8. Greater than 8, the next bar is at 9. So the probability, the bars would be these guys. Okay. Now in terms of the CDF, this would be 1 minus the CDF at 8. Okay. The CDF is inclusive of the number you put in. Capital B at 8, CDF at 8 is equivalent to probability less than or equal to 8. Okay. Okay. What about these guys? In terms of probability first, this is the probability of x between what and what? Okay, so you're saying 6 inclusive? Okay, so it's greater, so probability of x greater than or equal to 6, but less than or equal to 10. Okay, or probability of x greater than 5 and less than 11. Same thing, discretely. Okay. Now, in terms of the CDF, what do you think?
You would do it of 10
Correct. So this would be CDF at 10, that's this area, minus CDF at 5, not at 6, at 5. So you're taking all of these minus all of these, and it's going to give you these guys. Okay? Okay, so an example. What is the probability that a salesperson gets a sale more than 2 times, well, let's say greater than example, more than 2 times in 6 sales calls if the probability of getting a sale on any given call 50%. So each trial has a 50% success to get a sale or not. We're doing 6 trials, so 6 calls. What's the probability of getting what is the probability gets a sale more than 2 times? So P of X greater than 2, right? So we're evaluating P of X greater than 2 times, okay? So now you can reason about this in any way you like. Draw a good diagram if you want, put a bunch of bars and think about this, but always write it in terms of P and then convert it to binomial, all right? So P of X greater than 2, I'm thinking CDF, this is going to be, CDF is only going to be counting probabilities less than. So this is 1 minus P of X less than or equal to 2, and that's 1 minus B2, and you get that number. Okay? Now you can program these in your Python. Say option 1, probability exactly at a certain number, and then option 2, probability greater than a number, probability less than a number, or probability between 2 numbers. And just have the code do it for you, okay? Have the code reason about it for you. All right, the next one is the hypergeometric distribution. The hypergeometric distribution is one where we can deal with issues when the probability changes as we start picking and sampling from something. Okay, and that's essentially when you have no replacement. All right. It's similar to the binomial, but consecutive trials are dependent because possibly there is no replacement. Okay, so you're drawing, you're drawing from a deck of cards, but then you're not putting the card back, so that's changing the probability of success on the next trial, and so on and so forth. Okay, it's given this kind of fancy definition. You can derive this. I'm not interested in deriving that because it's not a course about probability. But I want to be able to use this distribution. Okay, it has a fixed number of dependent trials and a specific number of countable successes. So those are the conditions to declare a probability, to declare the hypergeometric and use it. And this will become clear once we do an example. I'll just do the formalities first. Each trial consists of selecting one of n items, n capital in the population, okay, and results in either a success or a failure. So one key condition here is that you know your entire population. Okay, so you're sampling from I'm sampling from this entire classroom. That's my population. I'm sampling people with a certain height or something, right? And so I need to know the entire population. So you need to know the capital N. The experiment consists of n trials. So how many times am I picking from the population? And that's going to be lowercase n. I know we use the same symbol. That's what they chose to do. I want to try to be consistent with textbooks. Now you also know the total number of possible successes in the population, and we're going to call that lowercase k. Now these are useful. There are problems like that where you're like, you have a bag of red and green marbles, and there are 7 green marbles out of the entire bag, right? So the number of green marbles in a 100 marble bag, and what's the probability of getting 2 green marbles when you select 13 marbles, right? So that will be the distribution that will answer this kind of problem. The trials are dependent because you're not putting things back in the bag, for example. And finally, the random variable x that you see here in the first argument counts the number of successes in n trials. And again, success could be defined in however way you like, but you got to be careful in how you compute what k is given to you. Okay. Excuse me. The symbol we'll use is lowercase h, and we always start with the argument x, and the standard in the literature is to put nkn, so lower n, lowercase n, which is the number of trials, so trials, number of successes, and then population size. Python is going to switch that order, and I don't know why they did it that way, but textbooks use this order, so I'm going to be faithful to the mathematical, to how the textbooks are using it. And finally, you are given the formulas for the, you can derive analytically what the mean and what the variance are for a population governed by the hypergeometric distribution. Okay? Just keep in mind, capital N, number of items in the population, lowercase n, number of trials, lowercase k, number of successes, which you know in the population, and x is the number of successes you're looking for to obtain in n trials, right? Which is going to hit Python directly. And from Python, you get this from SciPy, scipy.stats, import hypergeom. It's called hypergeom. And you call hypergeom.pmf like we did with the binomial. First argument is always x, but note here they flip the arguments. It's capital NKN, so population, number of successes, and then number of trials. In our math, we put the other way around. We put trials, successes in population, and then population size. Just watch out for that. If just write this once, follow this nomenclature. It's not documented at all. It's even they use other symbols, M, 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 K. It's incredibly complicated the way they symbolize it. Just use this approach. Okay, what I'm describing here, these symbols, anchor them in your mind. Do that one example in Python, and then just repeat over and over again. And again, we can also declare this in a variable and then call it over and over again, call the PMF over and over again. I'm not going to plot it because the hypergeometric distribution has some weird conditions on the minimum and the maximum value, which you have to deduce from the combinatorics, that formulas that are up here. I just put this slide for your benefit if you want to know what the minimum and the maximum possible values for your successes on the x-axis. So it's just a little annoying to plot. So I'm not going to plot it, but we will work directly with some examples. We'll start with the first example. At the local grocery store, there are 20 boxes of cereal on one shelf. That's my population. Okay, that's my population. Half of which contain a prize. That's the probability of success. Okay, k is equal to 10, right? So my population, capital N, is 20. My k, the number of success, it's a number, it's 10. They have a prize, because my eyes is on the prize. And suppose that you buy 3 boxes of cereal, so those are your trials, right? Buy 3 boxes of cereal. What's the probability that all 3 contain a prize? So my x is also 3. Okay? My x is also 3. So there are 4 variables here. 3 of them are given, the population size, the number of successes in the population, and the number of trials. And then your last one is x, how the number of successes you're tracking. So we're doing 3 trials because we're picking 3 boxes of cereal, and we're asking what's the probability that all 3 contain a prize. We could have asked what's the probability that 2 contain a prize, or 1 contain a prize, or at most 2 contain a prize. Okay? Now you can't ask for 4, it will crash, because 4 is going to be greater than the number of trials, right? And so here we argue like that this is a hypergeometric. Yeah, it is a hypergeometric. Consists of an outcome of success or failure, known population size dependent trial, number of successes in our sample. That's what we're tracking, x equals 3. Number of dependent trials is 3. So we're picking, once you pick the first serial box, you didn't put it back, right? So the next serial box, the likelihood of having a prize has been affected. What if the first one had a prize? So now you reduced how many prizes are left on the shelf. Number of successes in the population, k equal 10, and the population is 20, right? And then you can run this, and you can either use the formula or plug it into Python. And we're gonna plug it into Python. This looks like lowercase h, 3 semicolon 3. That's my number of successes. What's the probability of getting exactly 3 prizes, 3 boxes, and then I'm picking 3 boxes. There are 10 boxes with rewards and 20 boxes in total. You get a probability of 10.5%. So in terms of Python, that order is inverted here. Those first and last number are inverted. Population size, number of successes, 3. Just keep that in mind, okay? This will mess things up. So we'll do this real briefly in Python. From scipy.stats, import hypergeom, and then I will call hypergeom.pmf, and I'm going to put, so it might help to say, to just type the numbers here, put n equal 20, number of trials is 3, k is equal to 10, and my x is equal to 3. So hypergeom.pmf, x, and then n, k, n. Okay? And then you print this, it gives you 10.5% exactly as the number shown on the slide. Okay? Okay. There are 7 yellow and 9 green marbles. Again, just examples in a bag. If 5 marbles are chosen at random without replacement, what's the probability that exactly 3 of the marbles chosen will be yellow? So yellow is going to be our success. We have a total of 7 plus 9 marbles in the bag. Okay, so 16 marbles in total. And then 5, our number of trials, so that's my population. My number of trials is 5 marbles because I picked only 5 without replacing them. Okay. Now the probability of success is 7 because I'm tracking the number of yellow. I'm checking if my samples contain yellow marbles, right? So I know that in the population there's 7 yellow marbles. So k is 7. What's the probability that exactly 3 of the 5 marbles chosen will be yellow? And again, you can run this through, and what you need to know, capital N, population is 7 plus 9. That's the total number of marbles. We're picking 5 marbles, so my trials is 5. And I'm looking for 3 yellow marbles in those. But yellow is my indicator of success. And how many yellow marbles do I have in total? 7. So k is equal to 7. And you plug in the numbers, h3, semicolon 5, 7, 16, and you get 28.8. Same thing with Python. You can always notice that these two numbers are inverted, okay, or flipped. Similarly, with when we had probabilities less than or greater than, we can define those also for the hypergeometric distribution. We do an example. A shipment of 25 light bulbs contains 3 defective bulbs. If 5 bulbs are selected randomly without replacement, what is the probability that fewer than 2 of the bulbs chosen are defective? So my total population is 25, and I know that 3 of those are defective. Now defective is my success, and k equals 3. I know the total number of successes in the population. I'm going to choose 5 bulbs out of that. That's my number of trials. And then what's the probability that we get fewer than 2 bulbs are defective? Fewer than 2, that's less than, is strictly less than. That's p of x less than 2 strictly. Now, the hypergeometric has also a CDF distribution. And in terms of CDF, we're going to use capital H over here. In this case, that's going to be CDF at 1, because px less than 2 is equal to px at 0 plus px at 1. Okay, and that's the CDF exactly at 1, right? So that's p of x less than 2, which is CDF exactly at 1. I have 5 trials, 3 k equals 3 defective bulbs, number of successes in the population, total population size is 25, and that's exactly equal h lowercase h0 and PMF at 0 and PMF at 1. Okay, or probability of x less than 2, that's 90, almost 91%. Similarly, you can call the CDF on the hypergeometric distribution. So, same way we did with the binomial, just call these functions to calculate. I don't expect you to put this in your calculator. In your exam, you will be allowed to use your Python notebooks or Google Sheets, okay, or even your calculator if it has these functions built in. That's up to you to figure out, because you each have different calculators. You should, and you are encouraged to use the built-in PMF and the CDF. I leave that for you to figure out. If you're more comfortable using Python because you can visually see all the math you're doing, just use Python. We're good. If you want to do Google Docs or Excel, all of these functions are available in there. I cannot summarize all of them because they each have different names and use different symbols, etc. Right? So we'll stick with Python, but you're welcome to use whatever tool you feel comfortable with. I'm not going to be prescriptive that way. Okay. All right. So that would be the CDF, and then in this case, this would be the CDF exactly at 1. Okay, and also watch out for these numbers here: population, number of successes, number of trials. But our math formula puts it the other way around. All right. This is another example where, okay, yep, probability x less greater than 3. I'm not going to do it because I want to get to the to finish with distributions today. So you can work out this example. It's fairly consistent with the previous examples. And finally, one little trick here is that the binomial distribution can serve as an approximation to the hypergeometric distribution. It's not hard to compute either, but this is a mathematical result that people rejoice at having. And it's essentially that the binomial can be used to approximate the hypergeometric, because if you're doing this by hand, the hypergeometric is more annoying to calculate. It's easier to calculate the binomial distribution. And so you can approximate the hypergeometric as a binomial if the population size approaches infinity or is very large. In that case, your hypergeometric, remember, hypergeometric has 4 parameters in it, but binomial has 3. So somehow in that limit, we have to go from 4 to 3. And what happens, your k and n combine into 1 parameter. So now what is k over n? That's the probability of success, right? The number of k is the numerical value of the number of successes in the population. 7, 15, it's not a probability. And capital N is your total population. So k over n is your frequency of success or your probability of success, right? So that parameter changes. Another rule of thumb where you can use binomial to approximate the hypergeometric distribution is if your number of trials is less than your population divided by 10. Okay, you can then use the binomial distribution. Okay, the last distribution we'll talk about, I'm trying to get you out early today, I'm not sure, is the Poisson distribution. It's not the Poisson distribution or Poisson distribution. Okay, Simon Poisson, he's a French mathematician. He died in the 1840, I think. He came up with this distribution. Actually, one of the big research topics that my group does is on something called the pressure Poisson equation. So he came up with that nasty equation that's like very, very costly to solve. It's just a linear system of equations. You did numerical methods. You remember the heat equation, the system of equations you got in d2 t double prime equals something, right? d2 t by dx squared equals something. That's a Poisson equation in 1 dimension. Okay, so Poisson comes again. Poisson literally, if you know French, Poisson literally means fish. Okay, so you know Simon fish or the fish distribution. Okay, it doesn't look like that. The Poisson distribution is kind of nice and rounded, but it's an interesting distribution because it appears to be a continuous distribution, but it's not a continuous distribution. It is a discrete distribution. Wait until you hear about it. So it serves as a model for counts which do not have a natural upper bound. So it's something that could repeat over and over and over in time. Like, you know, how many times your internet breaks per hour, or you cannot log into your Zoom. How many times Zoom logs you out, you know, in a day, which is incredibly annoying. And then you have to log back in. You have to call like the president, and you have to log into Duo. And it's just like log in already, right? Yeah, it's very annoying. Thanks for agreeing with me. Always appreciate it. It's an important probability distribution. And the way, I don't know, the way they describe it, I have to read it every time. It describes the number of times an event randomly occurs in 1 unit of time. Now, 1 unit of time, you define that. Could be, again, how many times you observe a certain radon level in a day. Your unit of time is 1 day then. You declare what that is. Or how many times your internet connection drops in 2 hours, your unit of time in 2 hours. Or it could be 15 minutes. You define what that unit of time is. It doesn't matter. But there's no upper bound to how many times that occurs because it's a repeating process. Okay? In 1 unit of time, each instant can be regarded as a potential trial, essentially. So every time, every instant that's passing in that unit of time is like a repeating trial. You're not counting the number of trials. You're essentially getting the aggregate per unit of time, how many times this event is going to occur. Okay? All right. So it has the following formula. I know it looks continuous, but it's not. It's actually a discrete formula. And it's primarily because of that x factorial at the bottom. In the Poisson distribution, it's a discrete distribution number of possible successes over a given interval of time. So again, in all of these distributions, we're counting the number of successes. Binomial counts the number of successes and independent trials with a probability of success p. Hypergeometric, number of successes in n trials where there are k successes in the population of size n. Same thing with the Poisson distribution, is you're counting the number of possible successes, but over an interval of time. But it's not continuous. But that's what's cool about it. It's not continuous. It's discrete, so it's easier to work with. It has the following rules. Each success must be independent of any other successes. So whatever is happening in 1 unit of time is independent of what's happening in previous units of time. That's not always true, but when it is, you can use the Poisson distribution. The random variable x counts the number of successes in the given interval. Okay. Now we don't define, the formula doesn't define the interval, but what it defines is the average number of successes lambda in a given interval. Okay. So it doesn't. You don't define. You don't see 15 minutes here or 2 hours. It's not there. It doesn't. That doesn't matter. Because you're just counting, this is just strictly tracking the count per unit interval. All right. Now to track that, what's important is that mean value lambda, which you would know in your problem statement. That's something that needs to be as an input. And then we also know that the mean and the variance, they're equal. They're equal exactly to lambda. Okay. And those are the kind of properties of this distribution. So let's do an example. A barber usually finishes 1 haircut per 15 minutes. Okay? Calculate the probability that the barber is feeling extra speedy one day and finishes 6 haircuts in 1 hour. So we're looking, if he does, that's like me. I go there, he can finish 6 of me in like 1 hour, right? I'm really, really low maintenance. Just buzz my hair, I'm done, right? So I've actually had students who adopt my style. Like they have this lustrous hair, and then next year they're like all shaved up. I'm like, yeah, go sad, Okay, calculate the probability that our barber feeling extra speedy. So he averages 1 haircut per 15 minutes. So in 1 hour, that's really our interval because we're asking what's the probability of 6 haircuts in 1 hour. So that's my unit of time. Okay. Now what's my average haircuts per unit of time? We know he does 1 haircut every 15 minutes. So his average on a normal day is 4 haircuts per hour. So my lambda is 4. Okay. And I know my time interval, it doesn't show up, but I know the lambda. That's what matters. And we're asking what's the probability of finishing 6 haircuts? My x is going to be 6. The number of successes is going to be 6. Okay? And you simply plug in probability Poisson distribution at x equals 6. It's a very easy formula. It's about 10%, 10.5%. Okay? And let me see if I have this set up for you in Python. Ooh. Oh, I'm sorry, I didn't put the the Python for you here. Okay, well, we can do this in Python. And I didn't put that in the slides. My apologies. But again, PMF and CDF for the Poisson distribution, they're the same. Guess what you need to import from scipy.stats? Import Poisson. Import fish. Poisson. Yeah, good one. So Poisson.pmf. Now that's going to take only one, it's going to take two arguments, right? Those are going to be x and lambda. So my x is going to be 6 over here, and my lambda is equal to 4 haircuts, right? And then that's 10.42%, exactly what we saw in the, exactly what we saw here, right? And you can plot this distribution, and it's going to look nice, smooth distribution. We'll do a few more examples. Also, the Poisson distribution has a CDF, so the same rules apply. You're going to do the CDF when you have less than or greater than. For health reasons, homes in Utah need to be inspected for radon gas, which decays and produces alpha particles. One device counts the number of alpha particles that hit its detector. To a good approximation, in one area, the count for the next week follows a Poisson distribution with a mean value of 1.3. More like 1.3 particles detected in 1 week. So we're given that interval, we're given the mean value, you're telling you this is a Poisson distribution, don't worry about anything else. But then what's the probability of exactly one particle next week, probability of one or more particles next week, and the probability of at least 2 but no more than 4 particles next week. So we're doing all three, p of exactly some value, p less than, and p in between two numbers. Okay. So for the first one, probability of exactly one particle, x equal 1, my lambda is 1.3, so that's Poisson 1 at lambda equal 1.3. Very easy, very simple, and we can evaluate that. So we can do Poisson .pmf 1.3, and that gives me about 35.5%, 35.4%. The next one is the probability of one or more particles next week. So at least one particle. So first write it in terms of p of x is greater than or equal to 1. Agreed? And so that's going to be all of the probabilities starting from 1 all the way to the end of the Poisson distribution. All right? Now, because my PMF, my CDF only computes probabilities to the left side, is going to be 1 minus the probability of P of x equals 0. Exactly. Right? So that's probability 1 minus probability of x less than 1. And that one is the CDF at 0. All right? Okay, that's the CDF at 0. So 1 minus f, capital F, which is the CDF. And there's a 72.73%. There's a 73% chance of observing one or more particles next week. Why am I talking week? Because that's my Poisson distribution. My unit of time is 1 week. Lambda is tied into 1 week. Now you can't ask the question for 2 weeks. You'd have to find the lambda for 2 weeks. It could be 2.6 for 2 weeks, or it could be 1.5. I don't know. But stick with what you're given, okay? And finally, the probability that of at least 2, but no more than 4. So x is between 2 and 4. Less than or equal, less than, greater than or equal, less than or equal. And that gives you CDF at 4 minus CDF at 1. Agreed? So those are the bars in the middle. If you forget that, just draw a bunch of bars and then just highlight them just to fix that idea in your mind. Okay? I have a couple other examples, and I'll give you a break, and then we'll finish off with just a couple of things. Suppose that the dial-up internet connection at your house goes out an average of 0.9 times every hour, so almost defining the interval here. If you plan to be connected to the internet for 3 hours one afternoon, what's the probability you will stay connected the entire time? So we're given the average per hour, but we're going to extend this to 3 hours. It's risky, but you know, we're going to have to do it. We're going to have to multiply 0.9 times 3, right? So my interval is 3 hours, and my lambda in 3 hours is 2.7, okay? And then what is the probability of staying connected the entire time, okay? So essentially no drops whatsoever. So what's the probability of getting 0 loss of connection? So that's Poisson exactly at 0. And there's a 7%, oh my gosh, I almost said 6, 7. Let's get this over with. Let's resume. So I made a cute little table here for you to summarize these distributions. And I write the different distributions, binomial, Poisson, and hypergeometric. And check marks, they're all discrete distributions. Both binomial and Poisson assume independent trials, but the hypergeometric, it's not independent. When you have a replacement, or you're changing the sample space, and so it doesn't work with independent trials. Whether you have fixed number of trials or not, both binomial and hypergeometric have a fixed number. You're sampling 15 pieces, 15 batteries, taking 10 marbles out. But the Poisson, it doesn't have a limit on the number of trials. It's just a time interval, right? You would use the binomial for problems with a fixed number of trials, same with the hypergeometric, but here each trial is independent and only has 2 possible outcomes. The hypergeometric, unlike the binomial, each trial is independent to the other, but there's also 2 outcomes, success or failure. Here use problems with independent trials, but the success occurs over a given interval. It's not, the success itself is not discrete, but we're treating the number of the unit interval time as the as your discrete measure, okay? So we're going to ask a few questions next and see which probability distribution better fits the data. So we start with the first one. Based on data from an online search provider, a new company believes that its website is viewed 1,500 times a week. That's nothing. Right? I have students who have like 50 or 100,000 subscribers on. I don't know if it's something to be proud about, but what is the probability that in the next 4 weeks the company's website will be viewed more than 500 times? So what do you think? Binomial, hypergeometric, Poisson. Whenever I hear like a week or a unit of time, a month or something, that's Poisson. Yep, that's definitely Poisson distribution.
Because it's time for Sorry.
And well pronounced as well. Oh, why did you bring that up now? You got to go to gourmandise. You got to go to gourmandise now. Okay. And like we tell, so we speak French at home, and we tell, and we're like, my son's like, can I have a croissant? I'm like, no, it's croissant. No, croissant. And I'm like, ah. Anyway, but so it didn't work. It didn't work. Poisson, croissant. Assume that the proportions of in-state and out-of-state applicants to the university has remained constant for the last several years. And that 58% of applicants are in-state residents and 42 are out-of-state. What is the probability that the next 250 of the next 250 applicants, no more than 100 of them are in-state? So this is not Poisson distribution. Okay, there's a fixed number of trials. But now the question, are those trials dependent or independent? To tell whether you can model with binomial or hypergeometric, okay? And the applicants are not independent of each other. It's not like you apply and that takes away, there's no like limit to the number of spots that we want people to apply to universities, because you know we want all the money and all the student loans to come in, right? Okay, I'm gonna scratch that off of YouTube. but so they are independent trials. right? So that immediately goes to binomial distribution. And finally, if it's, we did Poisson, we did binomial, the last one has to be hypergeometric. So of the 500 programs printed for the University Opera, several contain coupons for the local coffee shop. Ooh. You know, of these coupons, 100 are $1 off coupons. Yeah, that's going to make a difference. And 50 for a free latte. Okay? 50 of them are for a free latte. Assuming that the different coupons are randomly distributed throughout the programs, what's the probability the first 50 programs are handed out? So question is success, are you going to get a coupon or not? When I hand out a coupon, I have less coupons in the sample, in the sample space. Hand another coupon, I have less. So the trials are dependent on each other. But there's only two outcomes, success or failure. So either you get a coupon or not. So it's going to be a hypergeometric distribution. Okay? Yes?
With hypergeometric, is it also, there's only two possible outcomes?
Yes. There's, only two. But you define what the success is. In this case, coupon or no coupon. And with that, we end the show. All right? Have a good weekend. Godspeed. We'll start on Tuesday with continuous distributions. Do your homework, okay? Thank you.